This is Jeffrey Pettit, and today I'll be presenting my team's work on creating a decision support framework for grid-aware electric bus charge scheduling. Cities across the world are investigating how they can electrify their public transit services. One challenge with electric vehicle fleets is managing their charging schedules. EVs generally have a shorter range and a higher charging or refueling time when compared to traditional vehicles. EVs also increase the demand on the power grid when they recharge, so a charging schedule should avoid overloading the grid. Energy prices also fluctuate throughout the day, so you want to avoid overspending on energy by charging at inopportune times. These motivate us to create an electric bus charge scheduling policy that minimizes the energy cost of running the system while ensuring it doesn't overload the power grid. To accomplish this, we've defined a grid-aware decision support framework for bus charging. This framework is underpinned by a simulation of the transit system. It's used to estimate the impact of different charging actions. The simulation has two major components. The first is a traffic simulator that models travel times and battery discharge rates of the buses as they go about their routes. This is used to estimate when and where buses will need to recharge. The second component is a grid impact model. This uses GridLab-D to simulate the power grid of the city and captures the impact different charging actions will have on the power grid. This simulation is used by a decision-making agent, which evaluates potential charging schedules by estimating their long-term impact using the simulator. It will then choose the schedule that maximizes the expected reward, which we define as a combination of the energy cost to run the system and the power grid impact score derived from GridLab-D. We also include a penalty term for any buses that fail or run out of charge during their routes. The trade-off parameter beta allows an operator to determine the weight between the energy cost and the power grid impact in their reward. For decision-making, we use the online Monte Carlo tree search algorithm, which has gained notoriety for its use in AlphaGo, the world champion defeating Go program. We use this online algorithm rather than popular offline approaches like reinforcement learning because of the dynamic nature of the transit environment. Traffic patterns change over time, and transit operators often change the schedule of the buses. And each time this happens, an offline approach will need to be retrained. Online algorithms are also more adaptable to random events, such as traffic accidents or road closures, since they can immediately be represented in the simulator, which is used in the online algorithm. To test the efficacy of our approach, we performed a case study using the transit system of Richland, Washington. We compared the results from our framework to those of a greedy policy. And what we found is that our framework can save up to 10% on charging costs while still improving the strain on the grid compared to the baseline. We also found that beta does allow you to trade off between the two parameters. So cities with robust power grids may choose to emphasize saving as much money charging as possible, while other cities may choose to sacrifice a bit and spend a little bit more on charging their buses, but with the benefit of putting less strain on their grid. The main takeaways of this proof of concept work are that electric vehicles introduce power grid strain. So when you have a fleet of them, you should be aware of the impact your charging has on the grid. We argue that a decision support framework that's underpinned by traffic and power grid simulations is an effective and adaptive management approach to such a system. And our exploratory analysis shows that such a framework can improve both grid impacts and energy costs to run a bus system for a mid-sized city. Our work motivates future work, including looking at how to optimally place the chargers along routes, testing the framework's generalizability to other cities, and integrating charge scheduling with planning the routes. We plan on examining these and also extending the work to paratransit in our ongoing collaboration with the Chattanooga Area Regional Transportation Authority. Thank you very much for your time.